Let's be honest, we spent the last many weeks studying all the ins and outs of quadratics, factoring, quadratic formula, parabolas, and everything in between so that we could apply it. Honestly, that's where most math topics are headed, to the application. And the classic application of quadratic concepts is projectile motion. Now, projectile motion is really any object that is thrown or launched into the air. But it's not just anything that's in the air. It's not a bird, it's not a plane. It's something that's launched or thrown, like a baseball or a golf ball. Now, the equation for projectile motion can look a little intimidating, but honestly, it's a quadratic. And quadratic, in case you're still not sure, means it's a parabola. Yeah, it's got that squared term. It's going to make the shape of a parabola. And if you think about the shape of a parabola and an object that is projected, the special points that we have studied, they all relate. Look, the vertex, it's probably the most important point. And what is it? Well, it has everything to do with a maximum height. Now, we got to be careful. The x value is not the maximum height. It's when it gets to the maximum height. It's the y value. It's the y value that actually gives you that maximum. What about the y-intercept? Isn't that kind of like where things start? In this case, how high it starts off the ground. And then your x-intercept or intercepts, well, they actually represent the ground. But again, the x value is when it gets to the ground. And since that's going to often represent time, that x value will be how long it took to get back to the ground. In other words, how long is the object up in the air? Now, the other x-intercept typically doesn't make sense because it's kind of backwards in time. So you'll find out that we're usually just finding that positive x-intercept. What are all the parts of this equation? We're not going to memorize these things, but I do want you to understand, working backwards, that the last number is going to be my initial height. This number in the middle here is going to end up being the initial velocity. Like how hard did you throw the object? And then negative 16 is a constant because, well, it involves gravity. In other words, it's always going to be that same value. Now, these three circled and noted numbers here, these are like your ABCs of your quadratic equation. Yeah, it's just the number in front of the square, it's the number in front of your regular term, and then it's your last number. It's your ABCs. Ready to do a problem? Yeah, we can do this. Okay, how about a golf ball that's hit from the ground? Now, if a golf ball is hit from the ground, we don't have to go searching too far to understand that it's going to follow the shape of a parabola. Now, I don't know exactly what that shape's going to be, but I do know that it's going to be projectile motion, so it's going to be some type of parabola. And what we can do is we can write an equation for this. You say we can. Sure, we can write an equation because it's just going to use that projectile model. Now, basically, the model is describing the height of the ball, and I told you it's always going to be negative 16, continuing t squared. And then do you see how the initial velocity of the ball was 80 feet per second? Well, that's going to be my next coefficient on t. Now, thankfully, the ball was hit from the ground, which is, I say thankfully, because we're able to put a 0 at the end of the equation. And the nice thing about 0 is it doesn't need to be written. So my quadratic equation is just negative 16t squared plus 80t. Now, when will the ball reach its maximum height? Well, we see that word maximum, and right away we want to think vertex. And when you think vertex, you want to think the opposite of b over 2a. Now, the opposite of b is the opposite of 80, and 2a is just going to be 2 times negative 16. So I get negative 80 over negative 32, and you can put that in your calculator. It comes out to be 2.5. Now, do you realize what we really just found? You see, we're used to saying that it's the x value, but you're going to just need to adjust that it's actually the time that is represented by x. So what we really found is 2.5 seconds. Yeah, that's the amount of time it took for the ball to get to its maximum height. We just answered question B. What is that maximum height? Well, what that's referring to is the y value. Now again, you're used to saying that y is going to equal, and then we'll find that answer, but we're just trying to make an adjustment that the y value is actually h. And what is h? It's just the height. So it's kind of like we're saying that the height at 2.5 seconds, yeah, we're going to plug in 2.5. So the height at 2.5 seconds, well, we got ourselves a little calculator problem. And you can pop this in your calculator and compute it real simply to be 100. Now what we just found is 100 feet. And to go back to my graph, what I really found is that at 2.5 seconds, my ball reaches a height. And if we go back to the graph, we find that what we really found is the point, 2.5100. Of course, it represents 2.5 seconds and 100 feet. Ready for this last question? Now it says, how many seconds will the ball hit the ground? When you see the word ground, you want to realize that we're talking about an x-intercept, because the x-intercept is always going to be when the object gets back to the ground. How am I going to do this? Well, we have to understand that the ground is represented by the number 0, specifically a height of 0. So if you think about your equation, that means that I can set it equal to 0. Isn't that something that we often do with these quadratic equations? Set them equal to 0? Sure. Now we just want to understand that that represents the ground. Now when you look at this equation, you have to think, well, how am I going to solve this? Probably with a quadratic concept. Now you could use the quadratic formula, but it's not necessary because I don't have this last number. What I mean is that you can actually solve this by factoring. Yeah, just try it with me. You can factor out a coefficient, or more commonly called the greatest common factor. So I can factor out -16, and I can factor out a t as part of my GCF. Now when you do that, that leaves you with t minus 5. And when you use a factoring technique, it's kind of easy then to just solve each factor equal to 0. Now think about it, this first factor equals 0 when t equals 0. But the second factor is going to equal 0 when t equals 5. What did we just find? We found the times when the ball is on the ground. Yeah, think about it with your sketch over here. At t equals 0, in other words, when this whole process starts, the ball's on the ground, and then when t equals 5. So are you ready to try a problem on your own? Well, I could understand if you're not, but you might be ready to think about this a little bit more. And if so, you can always pause the video. If not, I'm going to be, of course, going over this, and tomorrow you definitely are going to be doing some of these problems on your own as part of a class assignment. So what do we got here? We've got somebody trying to throw a set of keys up to their brother, standing 38 feet up on a balcony. Just a little side note, I would not suggest throwing your keys 3 or 4 stories up in the air, but it is a good projectile motion problem. And we can see the projectile motion formula, and what that means is that if we're going to try to draw a sketch, that we're going to have some type of parabola. So yeah, you don't need to go research too far. You should be able to draw a parabola. For this particular problem, we can specifically note that the starting value, yeah, the y-intercept is going to be 5. And if she throws it up in the air and it comes back down, it's probably going to look something like that. All right, so ready to find that maximum height? Again, it's a pretty classic question, and that always relates to the vertex. Now remember, we typically in the past would have said x equals, but we could always say t equals, just to kind of adjust to the new idea of this being the time. But it's still the opposite of b, and it's all over 2a. So I have -40 over -32. I can pop that in my calculator. Yeah, make sure that you are comfortable putting that in your calculator. You probably should break that into a couple steps so that you can correctly get 1.25. Now remember, that's going to be 1.25 seconds. So that's not actually the maximum height, but that's the time to get to that maximum height. The maximum height is actually the y value. And the y value comes from plugging in 1.25. And so again, we have pretty basic calculator step here. You just want to make sure you can put that in correctly as we've studied before. And that does come out to be, did you try it? Again, you should plug that in to make sure you can do it. Yep, it comes out to be 30, and that's going to be 30 feet. That's actually going to be my height. All right, you just found the vertex. You can label it if you want, but we just want to understand that 30 is actually that height that we were looking for. Will her brother catch the keys? Wait a minute, that sounds a little different than the previous problem. That doesn't have anything to do with the ground. No, we're not trying to find the ground. The brother's not standing on the ground. What's that you say? The brother's standing 32 feet up in the air? Yeah, he's standing up here 32 feet. Uh-oh, this is one of those situations where the throw is a little bit short, because the throw only, of course, goes 30 feet in the air. So no, he's not going to catch the keys. The throw is short. Sometimes a quadratic equation can be used to actually model just the path of the projected object. Now you say, well, I thought that's what we were doing. Well, technically what we were doing was having a quadratic equation model the time compared to the height of the object. But now the equation actually describes the actual pathway that the object is moving. Listen, it's gonna work just the same. Here, take this situation. We've got a batted baseball, and the path of that ball is given by this equation. Now notice that this equation is not officially in the projectile motion format, but it's still a parabola. Yeah. So can I draw that parabola with some confidence? I hope so. Let me try to show you how. For one thing, I can see that it is in the vertex form, so that means when I look at these numbers, I'm able to glean the vertex. Remember, the vertex is going to be the opposite of that inside number, and then, of course, is going to be the same as that last number. So could I mark 125 and 85? Yeah, that's going to be a vertex. And what else could I do here to help with my parabola? Notice that it's got a negative coefficient, so the parabola is going to open down. And yeah, it would be nice to have one other number here. You know, usually the y-intercept is something that we find. It's a little bit tricky in this problem because I can't just look at the last number and say it's the y-intercept. Instead, what I'd have to do is actually plug in a 0. Remember, when you plug in a 0 for x, you're finding the y-intercept. So put this in your calculator carefully, and you get y equals 3. What that does is that gives me some confidence that this parabola can start at the number 3. At this point, though, I can just draw the parabola opening down. And yeah, I mean, it still looks like an object that was projected because it was. It's just that now the equation is the actual pathway. Let's answer a question. Somebody's out in the outfield and catches the ball 5 feet above the ground. So somebody's standing out here in the outfield and they catch the ball 5 feet above the ground. How can I use that with my equation to find out how far the ball travels horizontally? Well, what you have to understand is that 5 is actually the y value. It's actually like the height of the ball. So I can not really plug in 5, but probably better said, I can set the equation equal to 5. And I want you to notice here that that means that I have the letter x to be solved. It's like I'm going to be solving this equation for x, and x is going to be the horizontal distance that the ball travels. Now, when you look at this equation, don't panic. You don't need to set it equal to 0 because it's in a special form. It's in that vertex form. Instead, what I can do is I can start to just do inverse operations. I can start to move numbers around. And of course, subtracting 85 from both sides would be my first inverse operation. Now that gives me negative 80, but that negative 80 right away is going to get divided by
Shane Lucian, if you're in the building, please dial 10011. Shane Lucian is on vacation. Thank you. John Lenhart, who is not on vacation, if you could dial 10011. John Lenhart, if you could dial 10011.
So when I divide both sides by negative 0.00512, that negative 80, that's going to turn into a nice round number, 16,000. Now 16,000 is equal to x minus 125 squared. And so here's kind of the key step in this problem. I'm going to do the square root of both sides. Yeah, this is one of those equations where I can use a square root method. Now the square root of 16,000 is not perfect, but it's equal to 126, and we could round it to about a half. That's nice because when you finish solving this equation, by adding 125, we can come up now with an answer that does represent the x value, which would be the actual horizontal distance that the ball traveled. So again, 251.5 is actually the x value, the horizontal distance that it took for this ball to reach that, again, to reach that height of 5 feet. When it was caught. Now for our last example today, I want to show you how a quadratic equation can help us solve a situation that's not necessarily a projectile motion, but just where some type of squared value is present. In other words, some type of other application. Okay, this is kind of a classic application dealing with a rectangular space. It looks like we're trying to fence in a pet llama. The space is going to be 480 square feet, and the length must be 4 feet longer than the width. I guess that is so the llama is happy. Now, at first look, it's like, whoa, what? I don't even know where to start with this problem. And that's actually kind of the hint here. You have to start with something that you don't know. You don't know the dimensions of this space. And so in math, when you don't know the dimension of something, you have the right to label it as x. It's basically an unknown dimension. But as soon as I label that one dimension of the square x, I'm able to label the other dimension a little more specifically. Remember how it said that the width has to be 4 feet longer? Well, that means that I could label this other dimension as x plus 4. And now all of a sudden I have a length and a width. And what do you do with a length and a width? Yeah, you can use them to find an area. How do you use them? You multiply them. Remember, area is always length times width. So if I multiply my two dimensions, which are x and x plus 4, if I multiply them, I can set them equal to the area. And I'm starting to create an equation. Not just any equation, but a quadratic equation. Yeah, as soon as I distribute x, that gives me my x squared. And looking a little bit here into the future, I'm going to want to move my 480 over here so that my equation is equal to 0. So if I subtract 480, make the equation equal to 0, I have myself with a classic quadratic equation. And how do we solve quadratic equations? Yeah, with any of the methods that we've learned. You could factor it, except I don't know if I want to try to factor something with this big number 480. So you could use the quadratic formula. That's right, I could solve this with the quadratic formula. I can do a little opposite of b, plus or minus the square root of b squared minus 4ac. So quadratic formula is nice. It can handle strange numbers. Again, something like this 480. But of course, you're still going to want to get that calculator involved, as we've said many times. Make sure that you can compute this value, 4 squared minus 4 times 1 times negative 480. Well, that comes out to be 1,936. Now, it's actually true that the square root of 1,936 is perfectly the number 44. How about that? So I perfectly can get negative 4 plus or minus 44 all over 2. And usually in a case like this, we would add 44, which is going to actually give us 40. Remember, it's still over 2. And then we would subtract 44, which would give us negative 48. And of course, that's also over 2. So what's going on with these two values? Well, one of them makes sense because it's positive. One of them really doesn't make sense. It's going to end up as a negative number. How do we know this? Well, remember, what you're really finding right now is not just some random number, but you're actually finding the dimension to this llama pen. So only the positive 20 is going to make sense for x, but the other dimension is 4 units longer, 4 feet longer, so that would, of course, have to be 24. Did I just find my dimensions? I think I did, and if I want to double check them, I could always take 20 times 24 and just kind of double check that that really does equal 480. Little fun fact, these are the only two numbers that are going to equal 480, such that one of them is 4 units longer than the other. I want you to practice some problems, and as I mentioned earlier in the video, tomorrow you guys are going to end up solving some of these as a class assignment for the application of quadratics.